full screen. All right. So welcome to the March meeting for both the Life Member Affinity Group of Central Texas and the Consultants Network of Central Texas, co-hosted with Denver and Fort Worth Life Member Affinity Groups this month. Just a reminder that we are very open. So for Life members, we're very open to hearing from anyone on this call about topics you would like us to cover in future meetings. And we are very open to having anyone on this call give a presentation. There are some suggestions down there for possible topics. These tend to be fairly high interest for all of our Life member groups, health and aging especially. I'm sad to say, but also suggest tours that we could go on. We do like field trips. This is the Life member team. I'm chairman this year. Tom Grimm's vice chairman. Tom's on the call. I'm also treasurer. Clyde Springen is our secretary. Kai's program manager. John Purvis is our webmaster, and Dennis Ferguson handles communications for us. Which brings us to the Consultants Network, and I can do this, Louis, or you could jump in if you want.
Go ahead and do it, Bill.
Okay.
Thank you.
The Consultants Network is another affinity group in the Central Texas section. This one more oriented to helping consultants, as you can imagine, with publicizing members' skills, sharing professional opportunities, and also having meetings like this one, which interests our members. When we get back to in-person meetings, which we really intend to do sometime this year, social networking will be part of the reason to be a member of the Consultants Network Affinity Group. Louis is the chairman for that. Jody Everett's our vice chair. I'm secretary for that group. Kai is program manager for that one as well. And Sergio Lieberman is member at large. We're looking for a webmaster for the Consultants Network. Louis is getting tired of maintaining the web page for us. And I think that's going to bring me, yes, so that brings me to an introduction of tonight's speaker. But Fawzi, I understand you have an announcement to make.
Yes, Bill, thank you so much. And I'm not sure, I did send one page to Kai. I don't know if
you can share the screen.
Sure.
If you want.
Yeah, please. So anyhow, we have been working in the last few weeks to anyhow secure a special guest speaker and from out of town, but not far away. And that's Scott Atkinson. And he really was kind enough to respond positively to our call. And he's really missed us so much that he would like to spend some time with us. So, we looked at the date, and March 30th seems to be ideal for him. He may come earlier in the day to spend some time, but then we booked the American Asian Center, I think, for the evening, and we'll have some sort of food and beverage and networking as well as the talk. However, the most important thing, of course, is the topic. And as you know, if not all of you will know, Scott is very passionate about communications and has been working in communication for many, many years. And he has a great passion to, connect with people, and especially those who have been in different satellite space shuttles, and talk with them. So he will bring his experience, his own approach to it, and he loved to have that as in person, which makes a big difference. And for us will be a breakthrough, because that will be icebreaker for us to have in-person meeting for after a long time. We have been meeting at the AT&T for many years, and as of this moment, actually AT&T is still closing the doors. so we cannot still hold an in-person meeting. So we're fortunate actually to, for Scott to accept that. So we'll be happy to have him. And I don't know if we have the screen or you want me to.
Yeah.
I could
Well,
send it.
Yeah, it's up to you. You share screen, then you can do
Oh,
that.
I share the screen. I see. Let me see here. Let's see if I can share this screen. I'll actually share the desktop and see what happens. There we go. Desktop. Open system now. Allow them to share the screen, yes.
Yeah, I'll set up a multiple screen,
Oh,
multiple sharing.
screen recording. No, that's not what I want.
Yeah.
I'm not
But,
sure. It's not
No,
really.
it's okay. I think you already verbally tell us what's
I
happening.
did forward it, but essentially the essence of it,
Yeah.
I could read you quickly I mean, he will talk about space communications review, and he really focusing a lot on about the infrastructure, how it is supporting all aspects of equipment and tools and components, and how they are working together, and how it is sustained throughout the whole mission itself from beginning to end, in terms of setup, in terms of operation and maintenance and so on. So, and this is all for NASA's part of NASA's reliable space communications and navigation. It's called SCAN networks.
Mhm.
And as said, it's the backbone of all NASA's space missions and providing critical communication services for all Earth space science and human space missions. This includes all telemetry and tracking and commanding required by each spacecraft to transfer key data to the ground systems to manage space operations. That's a nutshell in terms of the talk. As I said, he loved to express himself and share his experience because of his engagement and involvement with that. So that should be really quite an interesting event. Again, it is March 30th.
Yes.
Probably we'll get into the center around 4:30. May have a networking opportunity at the beginning till maybe 5:30 or 6 o'clock, and then we'll move into the talk for about an hour and 15 plus Q&A, and then go for more networking. We'll have some other surrounding type of activities and news that we will share, but we'll leave it till that moment. So that's essentially in a nutshell what we're able to do. I'm thankful that appreciative the life member and as well as the consulting networks are also part and co-sponsoring that activity. It's free for everyone. There's no cost.
Yes.
And you just come and enjoy the evening and networking, and hopefully we'll all learn something and appreciate what the communication peoples are doing in with respect to satellite. Thank you.
Okay, good. Thank you. Thank you. So, Bill, you have the floor, and
We'll be sending the V tools and so on so that
Right,
everyone
yeah.
can register.
you set up the announcement. We all see it to
Yeah.
all the members,
Sure.
and the member can pass on to the friends.
Please.
All right, so
Thank you,
one
Carl.
last slide and we can get to tonight's main event that we're all tuned in for. Speaker is Drew Barbier of SiFive Incorporated. Worked in the industry for over 15 years. He's, I guess, Mr. Outside. He faces customers. He works with the customers, and has been with SiFive since early 2017. Currently Senior Director of Product Management, responsible for SiFive's RISC-V core IP portfolio. The title is RISC-V and Unlimited Future. And with that, we can turn it over to Drew.
Yes.
All right, thank you.
Yes, Drew, you can share your screen.
All right. Is it coming across?
Yes, we see it now. Yes.
All right. Thank you for the introduction, and Yeah, I have a picture of a rocket ship. We don't actually make things that go into space, so maybe not quite as exciting as Mr. Scott's talk. But we were recently selected by NASA for their high performance space computer processor. So still related to space in some ways, but I'll tie it all together in a bit. But really, this talk is about RISC-V, sort of the origin story for RISC-V, why it's so popular. And then towards the end, I have a little bit about SiFive's product portfolio that I'll sort of talk about and let you know, everything that we're doing at SiFive specifically. Please feel free to jump in with questions. I give these kinds of talks all the time, although this material came from Mr. Krista Asanovic, so I want to thank him before I start off. My current role as Senior Director of Product Management, I do a lot of product pitches and interactions with customers as well as our own engineering team. But Krista was really part of the origin story, as you'll see, for the RISC-V ISA. And he gave a talk about 5 months ago in Cambridge, UK. And I stole a lot of the slides from him because I felt that was more relevant for the discussion and what was being asked for tonight. But for those of you who don't know, Krista Asanovic is a tenured professor at UC Berkeley. He's also the chairman of the RISC-V Foundation and also the founder and chief architect at SiFive. So he has a lot of titles. He's a very passionate and interesting man. I put a link to the YouTube video here. If you want to see a different version of the intro slides done and probably a better way. First is a really inspiring speaker, so I would recommend checking out some of the lectures that he's done in the past. So that's Krista. Who am I? So I gave the intro. So my name's Drew Barbier. I run the RISC-V Core IP roadmap at SiFive. So I'll talk a little bit more about SiFive a bit later. But I was a pretty early joiner to SiFive in March of 2017. So at the time, I think I was employee number 20 and probably the first employee who wasn't 100% engineering. I was, part engineering, part customer focused. I was also one of the few people at the time that had actual experience in industry, having come from ARM and Faraday. Most of the people at SiFive at that time were recent graduates from UC Berkeley, with maybe one or two other people who also had some industry experience, but mostly on the engineering side. So I came with sort of the customer-facing background and the IP experience, which is the direction where the company wanted to go. So with that, let's get into it. So I think it helps to level set and understand some history. Companies come and go, ISAs come and go. There's a lot of popular ones here from the late 80s and 90s and early 2000s. So DEC was probably one of the most famous ones. The DEC Alpha was a very elegant ISA. A lot of people thought that was going to be more popular and successful than it was. Certain companies stake their company on that ISA. Intel x86 is still around, but Intel has a lot of other ISAs that they've done throughout the years. So i960 was their more embedded focused ISA that's kind of gone. Itanium is sort of the most famous flop probably in the history of computing. But then there's others as well. So Spark. So Spark actually opened up their ISA, and you can see the IEEE version number here. But when Spark was acquired by Oracle, sort of development into Spark, it kind of closed down and teetered out. MIPS was also another very popular one. This was sort of the textbook ISA, textbook RISC ISA is taught in many universities still to this day. But MIPS, the company, had some success in the 80s, 90s, and early 2000s. But then as ARM sort of hit their strides in mobile, MIPS sort of teetered out as well. They tried to stay relevant by opening up a portion of their ISA in 2018, but having, probably too late at that time as RISC-V was already taken off. They didn't really find success, and then they closed it down again. And now MIPS, the company, is actually doing RISC-V IP designs today. IBM Power is another very popular RISC ISA. This one's actually still around and still shipping, although not nearly as large as some of the other ISAs that are around. But this was a proprietary ISA, and they opened it up with open power. But having said that, again, probably too late, because they did that around 2019, and RISC-V had already sort of taken off as that sort of first open ISA. And then others, ARM is probably the most successful here. Very successful throughout the 90s and early 2000s. Was acquired by SoftBank in 2016, and then announced to be sold to NVIDIA, which caused a lot of panic in the industry. I can personally attest to as part of SiFive. We never had quite the opportunity pipeline until NVIDIA announced that deal. But then the deal was canceled. Now they're going to IPO, so they're still around. But I guess the question is, the real investment here is in your software. Software is king. It's expensive. It's hard to change. So why would you entrust your software investments to a proprietary ISA that could go out of business at any time, or be bought or acquired, or have something else happen to it that's completely outside of your control? So really, if you look at the rest of the industry outside of computer architecture or ISA specifically, open interfaces are just accepted industry practice. IEEE facilitates a lot of this. So if you look at networking with Ethernet, this is an open standard. There's many free and open implementations. There's many proprietary implementations. Nobody's doing token rings anymore, right? Because Ethernet was good, right? It's a good standard. And it allows for a lot of flexibility and implementation, and it solves the task. Another one is graphics. So if you look at OpenGL and Vulkan, two very successful open APIs. There's many implementations. The implementations are varied, right? NVIDIA and AMD and Power VR and all these others can design to it. So if there's been all of these examples of open interfaces in the industry, why don't we have open implementations for instruction set architectures? So if you look at this a little bit further, if you look at an SoC, so this is an NVIDIA Tegra SoC from probably the early 2010s. You can see the big application processors, the ARM Cortex-A9s, but what you don't tend to see is that there's probably a dozen or so other ISAs that are implemented on these big complex SoCs. They do different functions: graphics processing, image processing, radios, security, power management, so on and so forth. And usually, because these are more specific and specialized functions, they're not run on the main application processor, because the main application processor is just not good for those kinds of tasks. It was designed to be a general purpose processor. So, if you wanted to do your audio DSP algorithm on this, you probably could, but it would be very inefficient at doing it. So these main application processors are just not flexible enough for these sort of accelerator and more niche functions on SoCs. So what tends to happen is more application-specific implementations of these functions happen, and they tend to be done with in-house tools or designed by an in-house team, either at the SoC company or at different IP vendors throughout the industry that are purpose-built for a specific function. And so with that, you license an audio DSP engine, you license a video decoder, and all of these things are different and incompatible. They have different ISAs, different compiler tools, different debugger tools, different software stacks altogether. So why do we need all these different ISAs? Why are they proprietary? Do they need to be proprietary? And why do companies that implement these proprietary ISAs keep disappearing, right? It's a big problem, and it's an expensive problem for the industry. And so this is really what RISC-V is trying to solve. What if there was one stable and free and open ISA that everyone could use for everything. And it sounds like a really big goal, but really that's what RISC-V is doing, and it's being very, very successful in the industry in achieving a lot of this already. So with that, let's get into a little bit of the background of RISC-V and how it was created. So I mentioned Krista being a tenured Berkeley professor. So in 2010, he was starting a research team, and they wanted to create really a vector processor. But in order to run the vector engine, they needed a scalar ISA that they could use to program the vector engine. And so with that, there were really only two choices at the time: x86, which was way too complicated, and on top of that, they had IP licensing issues from Intel not wanting to license x86 to a university or research team. And the other option was ARM, who was also very complicated, but at the time ARM also didn't have a 64-bit ISA. So this was back in 2010. It was before the ARM v8 ISA. And then on top of that, there were also IP issues, right? ARM's an IP company. They don't tend to like universities using their ISA for these types of projects. So with that, Krista assigned two of his grad school students, so Andrew Waterman and Yunsup Lee, to begin what they thought would be a 3-month project to develop a clean slate instruction set. And with that, they also leveraged David Patterson, who's also a Berkeley professor at the time. And with that, RISC-V was born. And so this was supposed to be a 3-month project, but really it turned into a 4-year project, where it culminated in May of 2014, where Krista and Andrew and Yunsup released what they considered to be the frozen base user specification. And this is one part of the RISC-V ISA, albeit the most popular part that most application software runs on. Since then, they've had many tape outs as part of the UC Berkeley project, as well as research publications along the way. So the name is called RISC-V, so it's not RISC-V, it's RISC-V. And the reason for that is because it represents the 5th major RISC ISA from Berkeley. So the first two original RISC date back to the 80s from David Patterson. They were actually assigned to chips that they taped out at the time. Then there were two other RISC, SOAR and SPUR, that came in the late 80s. And then the next one that came was when Krista and team did this in 2010 with RISC-V. And they actually meant for this ISA to be a practical implementation, not a research ISA that's nice for research, but impractical to actually realize in real implementations. And the reason for this is because Krista and his projects actually taped out these ISAs and put them in silicon to prove that they were viable and good ISAs for actual implementation. So the first tape out was in a chip that they called Raven that was taped out in 2011 on a 28 nanometer process. So this led to Hot Chips in 2014. So Hot Chips is a very popular industry event. And with that, Krista and his sort of group of university researchers went to Hot Chips to talk about RISC-V publicly and to promote it. And I think that was a very useful exercise for them, because it sort of opened their eyes up to a lot of things that were going on into the industry, as well as realizing a lot of potential that they had in this RISC-V ISA and the desire for an open ISA standard that's not governed by any single entity or company. So he got his research team together. So Krista is here in the middle, if you can see my mouse. Yunsup and Andrew are here on the front right. You can also see Dave Patterson accompanied them as well to the event. And in the event, they got a lot of useful feedback, and I think a lot of that would turn into some of the things that are now in flight now. So one being, they were approached by a lot of startup companies at Hot Chips who expressed a significant amount of interest in RISC-V, because if you're a startup company, especially at this time, getting a license for an ARM CPU, even some of the most simple Cortex M CPUs, they said was like a 6-month process or a 1-year process. And it was expensive. So time and money that they couldn't afford as a startup. The other bit of feedback that they got was, a lot of the major semiconductor companies came to them and said they really want to make use of this research, but they had concerns given that it was a university project. Just like proprietary ISAs, university professors come and go, their research projects come and go, and they didn't want to make substantial investments in software and in the RISC-V ecosystem if Krista and his research would just lose interest and move on to the next thing. So they took a lot of that feedback and really formed two major things came out of that. One is RISC-V International, and the other is SiFive. So I'll talk about SiFive later on. First off, I just want to focus on RISC-V International. So RISC-V International is an independent nonprofit entity that governs the RISC-V instruction set architecture. So all of the RISC-V specifications belong to this nonprofit entity. RISC-V International is based in Switzerland, and that was more of a symbolic gesture to indicate that RISC-V is not belonging to any one nation state or country. It is in fact international. And really the goal of RISC-V International is to accelerate the adoption of RISC-V to benefit the entire community of stakeholders. And what you'll see in the next slide is there's a large membership in RISC-V International. So anybody can join RISC-V International, be it companies or individual contributors. And what happens at RISC-V International, RVI, is this is where future specifications get discussed. It's also where things like the compliance suites and other technical deliverables like the Golden ISA simulator development all happens. RISC-V International also has responsibilities for engaging the RISC-V ecosystem and growing the RISC-V ecosystem, as well as engaging the community. So similar to IEEE, there's RISC-V meetups and things like that happen in Austin and really all around the world. And so, I think first and foremost, if you've gotten to this point, you've never heard of RISC-V, you still don't know what RISC-V is, this top left bullet tells you exactly what it is. It's a free and open instruction set architecture specification. And I think that's the key. RISC-V is not a processor core. RISC-V is not an open source processor implementation. RISC-V is a collection of architecture specifications that anybody can read and implement. There's a lot of specifications. It's not just one. So the way RISC-V works is it's a very modular approach to ISAs, where you have what they call a base ISA, which was ratified in 2014 and is unchanging. So even if you fast forward 10 years into the future and it's 2033, the base RISC-V ISA will be the same as it is today. But RISC-V does introduce new instructions and new capabilities and what they call extensions. And these extensions are what get discussed in the RISC-V International task groups and special interest groups. So this is, an eye chart of logos of companies that are in RISC-V International. It's not even close to being, the complete listing of companies. So it's something like 3,500 plus companies are part of RISC-V International now, including some of the biggest semiconductor companies in the world, like Intel, who joined RISC-V International last year. You also see the likes of Google and just about any other major semiconductor company in the world. But it's more than just semiconductor companies that are interested here. You see a lot of software tool and debug tool vendors. And the reason for this is because a lot of their customers are using RISC-V and they're just used to using the same tools that they've been using for years on, say, the ARM architecture or some other architecture. And so because their customers have moved to RISC-V, they've also moved to RISC-V and see this as new opportunities for growth and expansion. You also see some large software companies, EDA companies in here, really anybody who touches processors at sort of that boundary between software and hardware will have an interest, and lots of them are already part of RISC-V International. So if you look at RISC-V International, so in the middle, you have the RVI, RISC-V International, and they produce the ISA specifications. They produce the golden model for the ISA that all the companies use to test their compliance against, compatibility tools, etc. But there's also very large software and hardware ecosystems that are tied to RISC-V. So, and also what you'll see is it's not just tied to the open source ecosystem. So there's lots of open source tools. They're there. GCC is there, bin utils, all the C libraries and so on. But it's also the commercial software vendors as well. So people are making money in the RISC-V ecosystem and selling tools successfully in the RISC-V ecosystem. And that's true on the hardware side as well. So because the RISC-V specification is open, it means there's a lot of flexibility in what you can do with it. So it does mean that you can read the specification and create a completely free and open source implementation of that ISA. And we have examples on this bottom left box of a number of those open source implementations that are already in the market. So if you just go into GitHub and type RISC-V core, you're likely to get a list a lot longer than what you see here. And the reason for that is because it's interesting and it's the first time people can do this and not worry about hardware companies coming after them and suing them. But it's not just open source implementations. I mean, those are interesting. They're interesting for hobby projects and research projects and things like that. But there's also commercial implementations as well. And this is where SiFive plays. So we license commercial implementations of RISC-V for different application types. And we're not alone, right? There's at least a dozen on this sort of bottom middle box here. And this is something truly unique in the industry that hadn't happened until RISC-V. So when I go and try to license a RISC-V processor to a company, I'm competing against other RISC-V vendors, right? So it creates market competition, like true market competition, compared to what's been out there in the past with other ISAs, where you can only buy it from one vendor or license it from one vendor. The other interesting aspect of this, and there's a lot of public examples of this, are companies who take the RISC-V ISA and create their completely in-house implementation of RISC-V, and they might not even advertise this on their product. And NVIDIA is a big example of this. So every NVIDIA GPU that you buy today has several in-house custom NVIDIA designed RISC-V processors in them doing all kinds of different stuff. And the reason for this is, again, because software is king, right? Because there's a large and established software ecosystem around RISC-V, companies can leverage that software ecosystem and differentiate where they want to differentiate on the hardware side. Same thing for SiFive. You know, we'd love to license RISC-V processors to every company in the world, but there's no way that, you know, SiFive and our team of 600 engineers could create every possible interesting PPA point or implementation that customers would want. And so because of that, companies can go and build their own, or they can license other implementations from other commercial vendors and not lose that investment in software that they traditionally would have in the olden model, right? Where, you know, I talked about audio DSPs and the NVIDIA Tegra example. If you change your DSP provider, that means you have to change your entire DSP software stack. And that has a substantial cost, both in actual money costs, but as well as engineering time and effort to port that software to the new DSP stack. Whereas with RISC-V, you're able to leverage and reuse all of that software investment, no matter whether you buy the core from SiFive or build your own or buy it from somewhere else. And so, with that, the goal for RISC-V, and the modest goal, as Krista put it, is to become the industry standard ISA for all computing devices. And this was kind of a, when you create these types of groups and movements, you create these very lofty goals that sound impossible at the time. Even if you fast forward back to 5 years, this seemed impossible. But really, this is happening today, and it's happening a lot faster than what everybody expected. If you're doing a new design today and you're not tied to Android or some server or HPC application, chances are you're using RISC-V already. And if not, there's a good chance you will be in the coming years. So, this is a corporate slide that we have that shows how fast the ramp for RISC-V has actually been. And towards the end of 2022, Callista, who's the chairman of RISC-V International, put out a statement that she believes 10 billion RISC-V cores have been shipped by 2022. That is a significant amount of cores in such a short time. I mean, if you think about it, the ISA wasn't even finished 10 years ago in 2012, let alone to ship 10 billion cores of RISC-V by 2022. There's been a lot of big news as well. So at the RISC-V Summit, which is a big conference that's held by RISC-V International at the end of every year, Google presented a keynote where they announced that RISC-V would be an officially supported port for Android. So this makes x86, ARM, and RISC-V the only supported ISAs by Android. So this was another huge momentum shift for RISC-V and ecosystem, whereas before, we never even saw consumer or mobile as a potential to license cores into. Now we have significant interest from major players in these spaces now that Google is on board with RISC-V. And we think things are only going to speed up from here. So if you look at this report from Simico, who published this report in March of 2021, they're predicting by 2025, about 80 billion RISC-V cores will be shipped. So substantial growth for RISC-V. And as I mentioned, it's not just application processors, it's everywhere. Another reason for this, and Krista and his strong university background is a good reason for this, but now most of the major computer architecture books are now written teaching RISC-V. So the major one, Patterson and Hennessy, you can see on the left, that I used when I went to university, and that just about everybody else uses, is now using RISC-V. Andrew's authored some RISC-V books as well. It's officially supported taught ISA at most of the tier 1 universities and the Ivy League schools, Berkeley's and Stanford's and so on. And as those schools adopt RISC-V, just about all of the other universities are expected to follow. So what's happening is because it's taught in university, because it's getting adopted in industry, the question in 10 years from now isn't going to be why RISC-V. It's going to be why not RISC-V. It's going to be the case that everybody is familiar and comfortable with RISC-V and would rather have a really good reason for a certain processor requirement not to be satisfied by RISC-V than to look for a proprietary implementation. So why is RISC-V so popular? You know, a lot of times engineers sort of get bogged down in details. As Krista put it here, they don't see the forest from the trees. You know, especially myself, more on the marketing side, right? I'm in the speeds and the feeds every day, right? We want to know, you know, how our power is or performance is compared to other implementations out there. But RISC-V is not popular because of this, right? It's not because it's 10% better or 30% lower power. That could be true. It's really happening because of the business model. You know, the business model is new and really fundamental and changes the way people are working. So back in the olden days, you would pick your company, and that would determine your ISA, right? You would pick whether or not you wanted to work with an ARM or a MIPS or whoever, right? Tensilica. Whereas today, with RISC-V, you're now able to pick your ISA first. So I pick RISC-V, and then I could have all the different RISC-V vendors bid on my application, right? So it's a much different business model than what there was before. And it's really due to this being, you know, an open standard. So RISC-V being an open standard, being the first major open ISA that's out there and widely supported and adopted. So just building on that a little bit more, let's compare and contrast sort of the top 3 ISAs that are out there. So x86, can you buy chips? Yes, you can. He has here 3 vendors, but it's really only 2. You can buy chips from Intel or AMD. And if they don't have what you're looking for, you're basically out of luck. So you can't license the x86 architecture. You can't buy x86 intellectual property to integrate in your own SoC. You can't add your own instructions, and you can't find open source implementations. If you look at ARM, it's a little bit better. So can you buy ARM chips? Yep, you can buy a lot of ARM chips. ARM has been around. They've licensed their IP to a lot of different companies. Many Raspberry Pi single board computers can be had very inexpensively. Can you get an architecture license and build your own ARM core? You can. It's very expensive, but you can do that. You know, Apple being one of the biggest examples of that. Can you buy commercial ARM core IP? Yep, you can do that, but only from a single vendor, and that being ARM. Can you add your own instructions? No, you can't. They've changed this on some of their embedded cores, but for the most part, the big apps cores, the interesting ones, you can. And is there open source implementations of ARM processors? No, there's not. So if you compare these with RISC-V, can you buy chips? Yes, there's 10 billion RISC-V cores have shipped in the market. Can you get an architecture license? Well, you already have one. The RISC-V specifications are free and open. Anybody can read them and implement them. Can I buy RISC-V IP solutions? You sure can. You can buy them from me or from other RISC-V commercial IP vendors. Can you customize it and add your own instructions? You sure can. The ISA was designed to allow you to do that. Can you find open source RISC-V implementations? You sure can, including the original one from Berkeley called Rocket. You can go to GitHub and type RISC-V in and see a lot of these open source implementations. So RISC-V is the ISA that likes to say yes. So what about RISC-V completeness? So this slide is a little bit dated, so things have moved even further since this slide. But yeah, there were a large number of RISC-V extensions that were ratified in 2021 to add a lot of new capabilities. I think the biggest one being the vector extension, or V. So before the V extension, there were a lot of different scalar instructions, floating point, double precision floating point, things like this, bit manipulation. But vector was sort of the one big one that was missing for a while. But since it was ratified in 2021, the RISC-V vector extension has been very well received by the industry. As a matter of fact, one of the SiFive implementations in the X280 I mentioned earlier was selected by NASA as the next platform for their high performance space computer. So all of their space compute applications from satellites to drones and so forth and probes that go out into space will be based on the X280. And the big reason for that is because of RISC-V, the ISA. They view that as a long-term play because RISC-V is an ISA that they see is going to be around for the next century and beyond, right? When you're doing space applications, it might take 5 to 10 years to develop the satellite or probe that you want to send out, and then another 10 years to get to wherever it's going to go. And you need people to be around at the end of those programs that can still understand what's going on in the software and still program it and things like that. And NASA really viewed RISC-V and the powers of the RISC-V vector extension as being crucially important for those type of applications. There's a number of other ISA extensions here: hypervisor, scalar crypto, vector crypto, other extensions around IOM and Muse and interrupt architectures and things like that. So I think the key takeaway here is, I think, especially towards the end of 2021 and going into 2022, RISC-V can be viewed as being quite complete and comparable to the most modern ISAs out there, including ARM and x86. Okay, so one of the key criticisms that come up for RISC-V is because it's so modular and flexible and can be adapted for so many different applications. How do you manage fragmentation? And I think Krista has a really good take on this, and understanding first fragmentation versus diversity. So fragmentation is doing the same thing different ways for the sake of doing it different ways. And so the example here is left-hand drive versus right-hand drive. There's no benefit to one way or the other. They're solving the exact same problem. Just now, if you want to develop a car and sort of service the global market, you have to have two SKUs, one for left drive, one for right drive. Whereas diversity is something different and something good that's encouraged, and that's solving different problems, right? Getting around on a bike around your town is very efficient and quick and easy. But if you want to transfer 500 people across the Atlantic Ocean, a bike's not a good way to do that, right? You really want a jumbo jet for that. So diversity is really about solving different problems, whereas fragmentation is doing the same thing different ways. So how is RISC-V avoiding fragmentation? So first off, it's being enforced by the users, right? No one wants a repeat of vendor lock-in, and this really played out when NVIDIA tried to acquire ARM. This really scared the industry in that, their supplier is now a potential competitor. And despite what, companies like NVIDIA were promising, they didn't want to do business with their competitor, right? So nobody wants a repeat of that. And so, when we engage with customers, a lot of times when we're talking about new features and capabilities, some of the questions they ask us are, are these officially ratified extensions? And that the companies want to support the standard. They don't want to be locked in to a specific vendor's implementation. And then finally, on the software side, it's just expensive to support fragmentation, right? Every custom instruction or extension that gets added, that has to be supported in software for a long time. And remember, going back to one of the earlier statements, software is king, right? So software is very expensive. It's easy to do something once, but when you got to maintain that one thing for the next 10, 15, 20 years, it becomes very expensive to do that, especially while, introducing the next thing and trying to increase capability and performance and so on and so forth. So we really think, users don't want this. The software world doesn't want this. So we think it's kind of self-policing. We're not really seeing fragmentation in the RISC-V ecosystem today. So how do you manage diversity? So, it still doesn't change the fact that, RISC-V is very modular and extendable. You can add things, you can take it away. So there's really, it lists three things here, but it's really one way that we're managing this in RISC-V International, and it's what they're calling ISA profiles and platform profiles. So what it's saying is on the for the markets and applications that care about standard software, right? If I want to run a Linux distribution on RISC-V, I want it to run on a RISC-V processor, no matter whose processor it is, no matter where the implementation came from. And so for these types of ecosystems where you have large software repositories that are largely out of your control, right? You're not managing every package in the Debian repositories or the Red Hat repositories, for example. You really want to standardize on what the processor looks like and feels like, what the SoC looks and feels like. And so at RISC-V International, they're developing what they call ISA profiles. So this is RVA 20, RVA 22, 23, and so on. And so what these profiles are groups of RISC-V extensions that describe the base functionality of the processor. So which instructions are supported, which types of interrupt controller is supported. And then on the platform side, there's this OSA platform that stands for application processors, where it's standardizing on things like memory maps, peripheral sets, so you can always depend on a certain type of UART being at a specific address in the memory map, as an example. And in that way, RISC-V SoC vendors can implement SoCs that adhere to these profiles so that they can then run standard software on them. So things like Android, things like data center, Linux distributions, and so on. But that doesn't mean on the embedded side, where every gate counts, where every milliwatt counts, you're in full control of your entire software stack. You can add things or take things away or customize things as much as you want. So RISC-V is very flexible in allowing you to do that, but at the same time, through standards or managing support and diversity for these very large software ecosystems. Okay, the next section is more about SiFive side of things. So maybe before I start there, are there any questions on RISC-V? Okay, so I'll go through the next couple of slides a little bit faster so that there's some time at the end for questions as well. But yeah, so the next section is about SiFive. So I mentioned these three guys earlier on in the hot chips slide, but the founders of RISC-V are also the inventors of RISC-V are also the founders of SiFive. So they created the company in early 2016, and basically after Yunsup and Andrew graduated, they formed SiFive along with Krista. Since then, we've been designing and licensing RISC-V core IP in the industry since about 2017. We've also won several awards from the Global Semiconductor Alliance. So we're the most respected private semiconductor company in 2022. We actually won this award 3 times now. So 2022, I think, was the most recent time. I think we won it in 2018 and 2019 as well. So SiFive is a company. So we have 300 plus design wins. We have over 100 customers. 8 out of the top 10 semiconductor companies in the world license SiFive IP directly. We really have over 600 employees now, so it's about 650 employees. So fairly large company in terms of engineering. And our valuation, so we're still a private semiconductor company. We had our last round of funding in about March of 2022. And at the time, the valuation of the company is about $2.5 billion. So we've been doing this for a while. So, RISC-V is sort of catches the spotlight for SiFive because we're sort of the first RISC-V processor IP company. But we really have a number of things that make our company interesting. And one is the the way we develop IP, it's a little bit different than most other companies. We use different technologies in a lot of the industry, in that we use a much higher level hardware design language called Chisel. Chisel, you can think of it actually compiles down into Verilog, and then Verilog can be run through standard EDA tools and standard verification flows. But Chisel affords us a lot of capabilities and the infrastructure that we've built up around it over the past decade. And you can see that manifest in the SiFive processor portfolio that you can see here. So having been a company for 6 years, 7 years, we have a lot of RISC-V IP products that are already on the market. So I'll start with the bottom box called SiFive Essential. So these are the products we've been selling for, well, since I've been here in 2017. At least we started with a subset of these, but it's grown to what you can think of as basically 3 microarchitectures. So each column in the Essential family represents a microarchitecture. So 2 series is our smallest and most efficient microarchitecture. 6 series is our mid-range embedded product, and 7 series is our higher end embedded product. So dual issue superscalar design. Within the series, we have 3 different types of cores. So E cores are 32-bit embedded processors, S cores are 64-bit embedded processors, and then U cores are 64-bit application processors. So in the 7 series, we have all 3 types. 6 series, we have all 3 types. And then on the 2 series, we only have the 32-bit and 64-bit embedded processors. Moving up to the SiFive Intelligence box. So I mentioned the X280 being the processor that NASA selected. So that comes from our Intelligence family. And the X280 leverages the RISC-V vector extension. And it's really an interesting design point because it has a very efficient scalar core that sort of comes from the U7. But what it makes it interesting is that it has a significant amount of vector compute associated with it. And this really makes it suitable for a lot of AI applications, as well as data center applications, especially where the X280 is paired with these more fixed function accelerators. So there's in AI, a lot of hardware matrix multiplication that happens. What we find is that a lot of companies, including another public design win with Google, whereby they're using the X280 as sort of a companion to their TPU processors. So they're using the X280 as the interface to their TPUs, and they're doing pre-processing and post-processing before sending data to their TPUs, and that's enabling their fixed function hardware to be a lot more flexible and adaptable to new algorithms and data flows as they come out. And then we have the SiFive Performance family. So these are our high-end general purpose application processors. So you can think of these as competing directly against the ARM Cortex-A processors that are out there, the latest and greatest Cortex-As. And I'll talk a little bit more about these on the next slide. So we just had a big launch a couple months ago, and I'll tell you about that. And then finally, on the SiFive Automotive family. So automotive, if you're not familiar with, is a very hard application space to break into. There's a lot of requirements around resiliency and redundancy, certifications that can be acquired, different functional safety rating levels, and so on and so forth. So SiFive really tried to stay out of automotive, even though there was a lot of people asking for it. But at some point, especially around that NVIDIA announcement that they wanted to try to acquire ARM, that really drove a lot of automotive companies to look into RISC-V. And what they found was that the solutions at RISC-V were not just viable, but in a lot of cases better than some of the offerings that were out there. So SiFive's announced an automotive portfolio, whereby we're taking existing processors in the portfolio and making them suitable for automotive applications. So the performance family, so I touched on this a little bit, but the goal here is to not just be the best RISC-V processor on the market, but to be, the best processor period on the market, regardless of ISA. We see this with performance density as something that we see as being an advantage for SiFive, and a lot of that can be contributed directly to RISC-V, where there's a lot of examples where our implementations aren't just as good or in some cases even higher performance than sort of the ARM equivalents out there, but also much smaller at the same time. And so, a lot of this can be attributed to RISC-V, where it's a brand new architecture. There's not as much legacy baggage and support that they have to have in supporting sort of out-of-date modes and so on and so forth. So with that, so I mentioned the NASA and Google design ones already. Horse Creek is another one. So we had a project with Intel where they licensed a highest performance core at the time called the SiFive Performance P550. They taped that out in a leading edge Intel process, and that's going on a developer board that we'll have available towards the end of this year. That'll be sort of the highest performance RISC-V developer board that you can buy. So, it's not just small embedded cores that SiFive is going after. We're really going after high performance spaces as well. And we have multiple generation out of order products that we offer to do that. So this was the lineup that we launched towards the end of last year, with the flagship core being the P670. 12.6 second 2K6 per gigahertz is just a benchmark that we use to compare products against other products that are out there. But you can think about this as being sort of the same performance point as maybe a 2-year-old flagship smartphone. But what's awesome about these products are that, it's not just the performance point or the efficiency point. I mean, those are good, but those are just sort of the barrier to entry to get into some of these application markets. But they also have the feature set that are needed and expected by processors in these types of performance levels. So, I mentioned the vector extension, crypto extensions, support for virtualization in both the core as well as the SoC and IOMU and interrupt controllers, and implements the RDA22 profile that I mentioned before. And then WorldGuard, which is a system security solution in the RISC-V space. Intelligence X280. So I talked a little bit about this one already, so we'll speed up. But the Intelligence family is really looking at having a vector optimized implementation for the market. So it's a good companion core. This is a use case that we see a lot. But RISC-V vectors continue to be a very good implementation, a very good vector ISA, and probably a good topic on its own for something like this if you're interested. With the X280, we can do things like scale to 16 cores. But because it's based on RISC-V and it's a RISC-V application processor, it has very high vector throughput, but it also supports a lot of standard software that's out there, including Linux operating systems. So this is a very common use case that we find is that, a lot of times the competition here are dedicated DSPs, and while they might be better at certain functions, when it comes to ease of use, the X280 is just very easy for customers to get a hold of, to get software up and running quickly in a programming model that's very familiar to them, while still having incredible vector performance. We have custom interfaces. So again, this is a case of diversity being good. So we have a custom interface that we call our vector coprocessor interface extension. This really gives customers direct access to the vector register file. So remember, the X280 has 512-bit vector registers. So with this interface, this gives you the ability to transfer 2 registers every clock to your custom accelerator. So very fast data movement from the X280 to a custom accelerator. and also very efficient because it's not going out on main system buses. It's not spending multiple cycles in transit going back and forth. So just better all around in terms of performance as well as power efficiency. All while at the same time having a very simple programmer interface and access to the entire RISC-V software ecosystem. All right, and I think that's it for the presentation. So I'll stop there and take questions, I guess.
Thank you, Drew. There are a few questions on the chat box.
Okay.
Maybe we can do those first. Someone asked about if you have some links with more documentation and information.
Absolutely. So it's very easy. RISC-V.org. RISC-V.org. You can go here and you can get the entire specifications that are there. You can learn all about membership to RISC-V. But if you click here under technical, let me blow this up. Under technical, there's specifications. And you can go here and you can read all the ratified specifications, as well as specification status is somewhere I go to a lot. And this has the status of all the specifications that are in flight as well. It's also where you can sign up to be a member of the RISC-V International. Okay.
Great, thank you.
Thank you.
Then let's see, Vivek asked about, can you talk to the tool chain availability for different platforms and multi-thread support in the simulations and modeling for designers to use in SoCs?
Yeah, okay, so tool chains, almost all of them are there. So there's open source, so GCC is there, it's been there since 2017. LLVM is there, you can get it from upstream LLVMs. I think it's been there since LLVM 12 or something like that, so 2 or 3 years now. And actually an interesting aspect of that is Chris Latner, so the original inventor of LLVM, also president of SiFive for 2 years, so 2020 to 2022. So as you can imagine, we had a key interest in LLVM. On the debug side, all the open source stuff is there. All the commercial vendors that you're probably familiar with are there as well. So the likes of Waterbox and IAR and Seger and all those guys all support RISC-V today. What was the last part of the question? Multi-threading, I think.
Multi-thread support in simulations and modeling.
Yeah. Okay. Yeah. So, on the modeling side, it's supported by the likes of open source side with QEMU, but there's also commercial modeling vendors. So Paris has been a very big member in RISC-V International. I think all of these models are multi-threaded as well. So if you wanted to just write RISC-V code and simulator code, you can do that very easily. As a matter of fact, if you're on like a modern Linux distribution, you could probably just install the RISC-V QEMU implementation directly from your package manager. And any recent version of these have SiFive models as well, but also generic RISC-V models. It looks and feels just like any other architecture, any x86 or RISC-V. If you're writing C code, you're not touching registers of the hardware, like you wouldn't even notice it's RISC-V. Okay.
Great. Well, I have a non-technical question.
Yes, sir.
Where do you get funding for your work?
When do we get funding?
Yeah.
For SiFive.
Yeah. Okay.
For SiFive, yeah, for your group.
SiFive is VC funded. Yeah, so SiFive is VC funded. So you can go to our website and see some of our investors. We also, Sunder Hill, I think, was our initial investor. So you can imagine the Silicon Valley bank collapse was interesting for me a couple weeks ago, but I guess it was a big nothing as it turns out. But yeah, so we're VC funded, but we have public funding from the likes of Intel Capital, Qualcomm and Samsung are also public investors. So yeah, so still a private company, but our last round of funding was about a year and a half ago.
Drew, this is Martin Hunt from Coherent Logics. I wanted to ask about I know that the RISC-V doesn't maybe address multiprocessors, but it looked like you had a slide a few back that was talking about multiprocessors, and really interested in how you communicate with all the processors in a multiprocessor configuration.
Yeah, so SiFive as an implementation, so we've supported multi-core really since 2017. So you could actually go buy the first Linux capable multi-core RISC-V processor was a dev board we put out called the Unmatched. But we have coherent fabric that connects our CPUs together. It's called TileLink, if you've ever heard of it. So it's another publicly managed spec though by the CHIPS Alliance and not RISC-V International. But we use TileLink and proprietary implementations of the TileLink protocol to connect our processors together coherently. We also support different versions of the AMBA coherent protocol, so ACE and CHI, to connect up to third-party coherent interconnects. So we actually just put out a press release 3 weeks ago with a company called Arteris, who is a key player in this space. But yeah, so we have our own coherent interconnect that we use internally. We're leverage it extensively. We're updating it all the time. Things like NOx and coherent interconnects are all things we're implementing.
And where was the U54 in this diagram of your portfolio?
So that's a good question. So this U6, the 6 series, sort of replaced the 5 series that came before. So U5 was sort of our mid-range processor core that was right here. And when we came out with the 6 series in late 2021, it became the replacement for the 5 series, which is what the U54 belonged to.
Just a question now. NVIDIA, they do a lot of graphic applications. So they have their own DSP part, or you just talk to that portion with the RISC-V?
DSP?
How about the graphic?
Yeah, so in RISC-V, because it's modular, there's different types of extensions. So vectors is a big one. So we see vectors and DSP kind of playing in some of the same areas. There is another sort of low-end DSP ISA extension that's sort of in draft. That's called the P extension, and that's really meant for like lower-end microcontrollers that need to do some kind of DSP processing. Whereas vectors, on the RISC-V vector side, supports scalable vector lengths, so you can have small vector lengths of 64-bit all the way up to something like 2000-bit vector lengths. So you can do a lot of DSP applications with those types of with the vector extension. And really, this is relating this back to a SiFive product, something that we implement with the X280 being a 512-bit vector length. Whereas you see on the more recent application processors, we implement 128-bit vector lengths. And the reason for that is because we expect the markets we're targeting for X280 to do a lot of vector compute, whereas the more consumer-oriented application processors, we expect there to be accelerators in the SoC somewhere, but you still need some kind of vector compute to be competitive.
Okay.
But yeah,
So your
just to be
business
clear,
model
though,
is,
I don't think you're gonna, fixed function DSPs are really good. And I don't think you're gonna see RISC-V vectors replacing, very targeted DSPs. It's hard when something is ground up designed for a specific application like audio processing per se. But in AI and all these other spaces where you need vector compute, DSPs may not necessarily be the answer there, and that's where these types of vector extensions are having a lot of success.
okay. So it's a Wi-Fi, SiFive offering IP licensing only, or you do some design work for your customers?
We do IP only. So we did have a different part of the company that was called Open5.
Okay.
So we bought a company that was called Open Silicon at the time, who did ASIC design services. And so we really maintained them as two separate business units, but
Okay.
in mid-year last year, we actually sold off the Open5 portion of the business to a company called Alphawave out of the UK. So now SiFive is just a pure play IP company. So the 650 people I talked about, that's all on the IP side.
Okay. Good. So any more questions from the audience? Yeah, if not, then we'd like to thank you, Drew, for such a great talk on a good topic. We know much more about RISC-V, and so just gonna add that just a note that Motorola used to offer RISC microprocessor also for a few years before they go big time with the PowerPC partnership. You fly a Boeing 777, that's a RISC chip there, Motorola RISC 80K. But that's easy now.
Did Nazar help with this one too?
Yes.
Okay.
Thank you. So any other questions from the audience? If
And
not,
question, Kai,
sure.
Has the technology really being adopted for mobile devices such as AR, VR, XR, which are really like a hot type of devices these days?
Yeah. So I can say on the embedded side, absolutely. So there's a ton of chips and controllers that go into like the goggles and stuff. Absolutely, those already have RISC-V. As for the main AP cores, Google made the Android announcement a couple months ago when we launched the P600 and 400 cores that I talked about. We had very strong quotes from Samsung and Qualcomm, and with all the stuff going on with Qualcomm and ARM at the moment, I'll leave it to your imagination to guess where they're heading.
All right. Thank you.
Okay, Louis or Bill, any other questions?
No, that's all I've got.
Yeah, that looks like it.
Thank you so much for the opportunity to speak, and I'll send a copy of the slides to you, Kai.
Yeah, thank you. Yeah, actually, I'm trying to ask you for that. Yes, great. Yeah, that's great material. So we learn a lot.
Thank you.
Okay, actually, the
Yeah,
five.
thank you very much.
Actually, what's the meaning of the five? RISC-V?
Oh, what was the meaning of the 5? Okay.
Yeah.
So I'll tell you the story they tell everybody, and I'll tell you the real story.
Okay.
So the story they tell everybody is that it was the fifth. Oh wait, I'm not sharing my screen anymore. Let me pull it up.
Okay.
It was the fifth implementation of the Berkeley RISC architecture.
Oh, okay.
And this is somewhat true, right? So if you look at the ISA for RISC-V and compare it to SPUR, there are some similarities there.
Okay.
But the actual reason is that they wanted to make a vector processor, and they needed the scalar part of that. They needed a new ISA because they couldn't use x86 or ARM. And so the V actually stood for vector. at the time. But they
Okay.
didn't- RISC-V became so popular, they didn't get a chance to do vector until much later. So the vector extension, it plays such a big part of the ISA, but it wasn't ratified until 2021. So vectors came much later.
Okay. Yeah, that's great.
Yeah.
Yeah, good story.
But the official reason is because it's the fifth RISC implementation from Berkeley.
Right, the 5th generation. Yes.
Yeah.
Okay, great. Okay, now thank you guys. Drew.
Kai,
thank
Kai,
very
are you
much. And,
Kai, are you gonna post the video?
yes. Just
I'd
publishing
like I'd like a link to the video when you get it.
yeah, we're publishing our website, in both websites. Okay, in 1 week or so.
Okay,
All right. Thank you for joining us, Gene. Yes.
thank you.
Okay. Good night, everybody.
Thank
Thanks,
you.
all.
Thank you.
Yeah.
welcome.
Appreciate
Okay.
that.
Bye.
Thank you.
Bye.